For decades, the search for life beyond Earth was guided by a single, rigid profile. We looked for rocky planets at a specific distance from their stars, the Goldilocks zone, where temperatures allow liquid water to pool on the surface. This narrow set of criteria made Mars our primary focus. We spent decades landing rovers and mapping its surface because it was the closest physical match to Earth, despite being a frozen, irradiated desert. But the data coming back from our furthest probes suggests our definition of a habitable world has been far too restrictive. Biology may not actually require a sunlit, rocky surface to take hold. Instead of searching for another Earth, astrobiologists are shifting their focus hundreds of millions of miles into the outer solar system, to the freezing moons orbiting the gas giants. By focusing exclusively on environments that mirror our own, we have likely overlooked the most common types of habitable real estate in the galaxy. Jupiter's moon Europa sits far beyond the reach of meaningful solar warmth. By traditional standards, a body this far from the sun should be a solid, geologically dead block of ice. But Europa is being manipulated by Jupiter's immense gravity. As it orbits, the moon physically stretches and squeezes, a process called tidal heating that generates massive amounts of internal friction. That friction creates a constant source of heat that radiates outward from the moon's core. It melts the bottom of the ice shell, maintaining a liquid water ocean that is estimated to be twice the volume of all Earth's oceans combined. We have direct evidence of this liquid interior. The Hubble Space Telescope captured images of enormous water vapor geysers erupting through the ice, proving that the moon's subsurface is active and under pressure. This environment shares striking similarities with Earth's deep sea. In our own oceans, life thrives around hydrothermal vents in total darkness, fueled by chemical energy rather than photosynthesis. Europa demonstrates that a world can sustain a liquid, habitable environment indefinitely using only gravitational energy. Solar light is a luxury, not a requirement. Even further out, Saturn's moon Titan presents a different challenge to our assumptions. It is the only other place in the solar system with a dense atmosphere and a visible weather cycle of clouds, rain, and rivers. However, at nearly 300 degrees below zero, the liquid on Titan's surface isn't water. The lakes and seas carving its landscape are composed of freezing liquid methane and ethane. Using the ALMA radio telescope array, scientists identified a molecule in Titan's atmosphere called cyclopropionylidene. It's a rare, highly reactive carbon-based loop that can serve as a precursor to the molecules that form the backbone of DNA. To exist in methane, life would need a different kind of structure. Researchers have modeled inside-out cell membranes that utilize the unique properties of methane to maintain the same protection and flexibility that Earth-based cells get from water. These theoretical azotosomes remain stable and functional even at the cryogenic temperatures of Titan's surface, suggesting that biochemistry can adapt to solvents that would be instantly fatal to earthly life. Titan proves that liquid water is just one of many possible mediums for complex chemistry. As long as a world has a stable liquid solvent, the ingredients for life can potentially organize and react. These theories are now being put to the test. NASA's Europa Clipper mission is designed to conduct dozens of close flybys, using ground-penetrating radar to measure the exact thickness of the moon's ice and sample the chemicals being vented into space. Following close behind is Dragonfly, a robotic rotorcraft designed to fly through Titan's thick atmosphere. It will spend years hopping between different geological sites to hunt for chemical signatures of biology in the methane sands. These missions are specifically built to recognize life that looks nothing like our own. They are looking for the metabolic markers of organisms that have evolved in the freezing dark and the liquid methane rain. These multi-billion-dollar commitments represent a total redirection of our exploration efforts, moving away from the hunt for Earth-like planets towards the most extreme environments in our neighborhood. The implications of this shift are massive. If life can persist on these outer moons, the number of potentially inhabited environments in the Milky Way effectively doubles, as gas giants and their moons are far more common than Earth-sized planets. In many ways, these subglacial oceans are safer than Earth's surface. Thousands of feet of ice act as a permanent shield, protecting any internal biology from meteorites, solar flares, and deadly cosmic radiation. We are beginning to see a galaxy filled with isolated, thriving worlds, hidden under miles of ice and illuminated only by internal heat. Our first encounter with another biology likely won't happen on a sun-drenched green planet. It will likely take place in the freezing dark of our own solar system.